In calculus, and more generally in mathematical analysis, integration by parts or partial integration is a theorem that relates the integral of a product of functions to the integral of their derivative and antiderivative. The rule can be derived in one line simply by integrating the product rule of differentiation. If u equals u and du equals u dx, while v equals v and dv equals v dx, then integration by parts states that, or more compactly, more general formulations of integration by parts exist for the Riemann-Stieltjes integral and Lebesgue-Stieltjes integral. The discrete analog for sequences is called summation by parts. Theorem. Product of two functions. The theorem can be derived as follows. Suppose u and v are two continuously differentiable functions. The product rule states, integrate both sides with respect to x, then apply the definition of indefinite integral, gives the formula for integration by parts. Since du and dv are differentials of a function of one variable x, the original integral uv dx contains v. In order to apply the theorem, v must be found, and then the resulting integral of u dx must be evaluated. Product of many functions. Integrating the product rule for three multiplied functions, u, v, w, gives a similar result. In general for n factors, which leads to where the product is of all functions except for the one differentiated in the same term. Visualization. Define a parametric curve by equals g. Assuming that the curve is locally 1 to 1, we can define the area of the blue region is similarly. The area of the red region is the total area. A1 plus A2 is equal to the area of the bigger rectangle, x2 y2, minus the area of the smaller one, x1 y1. Assuming the curve is smooth within a neighborhood, this generalizes to indefinite integrals. Rearranging. Thus integration by parts may be thought of as deriving the area of the blue region from the total area and that of the red region. This visualization also explains why integration by parts may help find the integral of an inverse function f-1 when the integral of the function f is known. Indeed, the functions x and y are inverses, and the integral x dy may be calculated as above from knowing the integral y dx. Application to find antiderivatives. Strategy. Integration by parts is a heuristic rather than a purely mechanical process for solving integrals, given a single function to integrate. The typical strategy is to carefully separate it into a product of two functions uv such that the integral produced by the integration by parts formula is easier to evaluate than the original one. The following form is useful in illustrating the best strategy to take. Note that on the right-hand side, u is differentiated and v is integrated. Consequently, it is useful to choose u as a function that simplifies when differentiated, or to choose v as a function that simplifies when integrated. As a simple example, consider, since the derivative of lane x is 1, x, we make part u. Since the antiderivative of 1, x2 is minus 1, x, we make dx part dv. The formula now yields the antiderivative of minus 1, x2 can be found with the power rule and is 1, x. Alternatively, we may choose u and v such that the product u simplifies due to cancellation. For example, suppose we wish to integrate. If we choose u equals lane, sin x, and v equals sec 2x, then u differentiates to 1, tan x using the chain rule and v integrates to tan x, so the formula gives. The integrand simplifies to 1, so the antiderivative is x. Finding a simplifying combination frequently involves experimentation. In some applications, it may not be necessary to ensure that the integral produced by integration by parts has a simple form. For example, in numerical analysis, it may suffice that it has small magnitude and so contributes only a small error term. Some other special techniques are demonstrated in the examples below. Polynomials and trigonometric functions. In order to calculate let then, where c is an arbitrary constant of integration. For higher powers of x in the form repeatedly using integration by parts can evaluate integrals such as these. Each application of the theorem lowers the power of x by 1. Exponentials and trigonometric functions. An example commonly used to examine the workings of integration by parts is here. Integration by parts is performed twice. First let then. Now, to evaluate the remaining integral, we use integration by parts again, with then. Putting these together, the same integral shows up on both sides of this equation. The integral can simply be added to both sides to get, which rearranges to, where again c is an arbitrary constant of integration. A similar method is used to find the integral of secant cubed functions multiplied by unity. Two other well-known examples are when integration by parts is applied to a function expressed as a product of 1 and itself. This works if the derivative of the function is known, and the integral of this derivative times x is also known. The first example is ln dx. We write this as let then, where c is the constant of integration. The second example is the inverse tangent function arctan. Rewrite this as now let then, using a combination of the inverse chain rule method and the natural logarithm integral condition. LIATE rule. A rule of thumb proposed by Herbert Kasub of Bradley University advises that whichever function comes first in the following list should be U.L. logarithmic functions. Lane x, log(x), etc. I. Inverse trigonometric functions. Arctan x, arcsec x, etc. Algebraic functions. x2, 3 by 50, etc. T. Trigonometric functions. Sin x, tan x, etc. E. Exponential functions. X, 19x, etc. The function which is to be dv is whichever comes last in the list. Functions lower on the list have easier antiderivatives than the functions above them. The rule is sometimes written as detail, where d stands for dv. To demonstrate the LIATE rule, consider the integral following the LIATE rule. U equals x and dv equals cos x dx, hence u equals dx and v equals sin x, which makes the integral become which equals. In general, one tries to choose u and dv such that do is simpler than u and dv is easy to integrate. If instead cos x was chosen as u, and x dx as dv, we would have the integral which, after recursive application of the integration by parts formula, would clearly result in an infinite recursion and lead nowhere. Although a useful rule of thumb, there are exceptions to the LIATE rule. A common alternative is to consider the rules in their ILATE order instead. Also, in some cases, polynomial terms need to be split in non-trivial ways. For example, to integrate one would set so that then finally, this results in applications in pure mathematics. Integration by parts is often used as a tool to prove theorems in mathematical analysis. This section gives a few examples. Using special functions. The gamma function is an example of a special function, defined as an improper integral. Integration by parts illustrates it to be an extension of the factorial, yielding the famous identity for integer z. Applying this formula repeatedly gives the factorial. Using harmonic analysis. Integration by parts is often used in harmonic analysis, particularly Fourier analysis, to show that quickly oscillating integrals with sufficiently smooth integrands decay quickly. The most common example of this is its use in showing that the decay of functions Fourier transform depends on the smoothness of that function. As described below, Fourier transform of derivative if f is a k times continuously differentiable function and all derivatives up to the kth1 decay to 0 at infinity. Then its Fourier transform satisfies where f is the kth derivative of f. This is proved by noting that using integration by parts on the Fourier transform of the derivative we get applying this inductively gives the result for general K. A similar method can be used to find the Laplace transform of a derivative of a function. Decay of Fourier transform. The above result tells us about the decay of the Fourier transform, since it follows that if f and f are integrable then, where, in other words, if f satisfies these conditions then its Fourier transform decays at infinity at least as quickly as 1 xi k. In particular, if k2 then the Fourier transform is integrable. The proof uses the fact, which is immediate from the definition of the Fourier transform, that using the same idea on the equality stated at the start of this subsection gives summing these two inequalities and then dividing by 1 plus 2 pi xi k, gives the stated inequality. Use in operative theory. One use of integration by parts in operative theory is that it shows that the increment is a positive operator on L2. If f is smooth and compactly supported then, using integration by parts, we have other applications for determining boundary conditions in Sturm-Liouville theory, deriving the Euler-Lagrange equation in the calculus of variations. Recursive integration by parts. Integration by parts can often be applied recursively to provide the following formula. This form is especially useful when v becomes 0 for some n. Hence, the integral evaluation can stop once the v term has been reached. Tabular integration by parts. While the aforementioned recursive definition is correct, it is often tedious to remember and implement. A much easier visual representation of this process is often taught to students and is dubbed either the tabular method, the stand and deliver method, rapid repeated integration, or the tic-tac-toe method. This method works best when one of the two functions in the product is a polynomial, that is, after differentiating it several times one obtains 0. It may also be extended to work for functions that will repeat themselves. For example, consider the integral let u equals x3. Begin with this function and list in a column all the subsequent derivatives until 0 is reached. Secondly, begin with the function v, and list each integral of v until the size of the column is the same as that of u. The results should appear as follows. Now simply pair the first entry of column A with the second entry of column B, the second entry of column A with the third entry of column B, etc., with alternating signs. Do so until further pairing leads to sums of zeros. The result is the following, which with simplification, leads to the result with proper understanding of the tabular method. It can be extended. Consider in this case in the last step it is necessary to integrate the product of the two bottom cells obtaining, which leads to and yields the result. Higher dimensions. The formula for integration by parts can be extended to functions of several variables. Instead of an interval, one needs to integrate over an n-dimensional set. Also, one replaces the derivative with a partial derivative. More specifically, suppose omega is an open-bounded subset of n with a piecewise smooth boundary gamma. If u and v are two continuously differentiable functions on the closure of omega, then the formula for integration by parts is where is the outward unit surface normal to gamma, is its ith component, and I ranges from 1 to n. Setting u equal to the constant function 1 in the above formula gives the divergence theorem for where 1 gets which is the first Green's identity. The regularity requirements of the theorem can be relaxed. For instance, the boundary gamma need only be Lipschitz continuous. In the first formula above, only u, vh1 is necessary. The other formulas have similarly relaxed requirements.